Hello, my name is David Minnen, and I'm a research scientist at Google. I wanted to thank the organizers of ICIP this year for inviting me to speak. And I'll be talking about current frontiers in neural image compression. Before we get started, I wanted to thank my team. The tech lead and manager is George Saderici, and my colleagues include Nick Johnston, Phil Chow, Johannes Bale, Eric Augustin, Sungjin Wang, Fabian Menser, Troy Chinen, and Saurabh Singh. I'll be talking about a lot of work from our team and outside of our team, and much of it comes from these guys. I'm going to start today by talking about learned image compression. I want to make sure we all have the same background to understand some of the developments. I'll talk about research themes and progress in the subfield, essentially as it's developed over the past 5 or 6 years. And then the bulk of the talk will be about rate distortion computation. Typically we focus on rate distortion, possibly rate distortion perception. I then want to talk about generative compression, which I think is a direction the field is going. And then I'll talk about promising research directions as I see it over the next 5 years or so. The basic architecture of all of the learned image compression models that we'll be looking at is a quantized autoencoder. So I wanted to go over the components in some detail to build a base of understanding. So this is a compression system, so we're going to have some kind of input image. There'll be the system itself, which we typically call a codec for a coder and decoder. And then there'll be some reconstruction or an output image. Here we're dealing with lossy image compression, which means the reconstruction will not perfectly match the input. The transform that goes from an input image into a latent representation is often called an encoder, and then a decoder is the opposite. It goes from a latent back to a reconstruction. And colloquially, we can call everything up to the compressed representation the sender, and everything after that, the receiver. That might be literal, you could be transmitting bits across a network, or it could just be that you're saving a file on a drive and playing it back later. It's important for all of these models that our representation is quantized. We need discrete symbols to work with the entropy model. That means that the sort of bottleneck of the autoencoder is going to be quantized. We'll have quantized latents instead of real valued latents. We'll then use an off-the-shelf entropy coder with a learned distribution over the symbols. That could be a Huffman coder, arithmetic coder, range coding, ANS. These all have speed and quality trade-offs, although they tend to get within a fraction of a percent of the optimal entropy. And the result of that is the string of compressed bits, which is your file that's saved or transmitted. We'll be using standard notation throughout this talk, so I wanted to go over the various symbols. The input image is typically X. The transform that maps X into a latent representation is called the analysis transform, typically G sub A. The latents themselves are called Y, and Y hat is the quantized version. And the transform that maps Y hat back to an image is called the synthesis transform, or G sub S. And the reconstruction is X hat. So we can say that Y hat is the quantized version of Y, and that is the quantized version of G sub A of X. And X hat is simply G sub S of Y hat. Since this is lossy image compression, X hat does not equal X, and instead we'll need some kind of measure of distortion that tells us how far away from X the reconstruction X hat is. And that can be any differentiable quality metric, such as mean squared error or structural similarity, and there's many other possibilities. We call the learned distribution over Y hat P of Y hat, and we're going to use that to entropy code the quantized latents. This leads to the full loss function, which we can understand as the familiar rate distortion trade-off. So negative log base 2 of P of Y hat is the entropy of the quantized latents. That's the rate that we want to minimize. Lambda is a trade-off parameter, and then the distortion is whichever distortion function, MSE, etc., that we selected. Okay, next we'll look at research themes and progress. I'll talk about how different researchers address the various components within learned image compression, and I'll highlight key publications that showed progress within the subfield over the past few years. This is our basic autoencoder structure, and to start, we'll focus on the analysis and synthesis transforms. Bale 2017 was one of the early learned image compression papers that introduced nonlinear transform coding. The structure of the analysis and synthesis transforms is fairly straightforward. There are 4 convolutional layers separated by GDN, that's generalized divisive normalization. The channel depth is 192 with a bottleneck of 320. And most papers follow this plus or minus since this paper was published. And every layer in the analysis transform downscales the input by 2x
So that means between the input x and the latent tensor y, we have a 16x total difference. So every column in y maps to a 16 by 16 pixel patch in the input image. In the synthesis transform, it's essentially the same in reverse. We use IGDN or inverse GDN, and the convolutional layers have the same depth, but they upsample. So it's transposed convolution instead of downsampling. Papers after this made the analysis and synthesis transforms much more complicated. So I won't go through every paper and every idea, but I will highlight a couple key papers. For example, Lee 2019 has a much more complicated encoder, so analysis transform. They also use dense blocks. So this is a block where the input and output of each internal block is concatenated. This has been shown to have a much richer representational capability. And they also use an importance map. So they had this idea that the network should learn how much of the quantized latents to use, like what's best from a rate distortion perspective. So they learn this binary map, and it has a multiplicative interaction with the latents. Jumping forward a bit, we have Guo 2021, which is a paper from earlier this year, and it actually gives the best rate distortion performance of any learned image compression paper that I know of. It again uses a much more complicated analysis and synthesis transform. Here we see residual connections, residual blocks. It uses split attention, which is a customized version of a local attention mechanism. It again uses two processing paths and a multiplicative interaction. So it stacks these together, and you have, I don't know, maybe 20 convolutional layers deep, so 5x what we had in the original Bali 2017 paper. And the end result is a much more powerful network. There are quite a few other ideas that different researchers have had on ways of making the analysis and synthesis transforms more powerful and more complex. I'm not going to go into the details of other papers here, but I will point you to this relatively recent survey, Learning End-to-End Lossy Image Compression, a benchmark. That's Hugh 2021. And they discuss a wide range of papers. And people have tried multi-scale approaches. GRDNs, or grouped residual dense networks, is a popular addition to the synthesis transform. It's often used for post-processing and came out of the image enhancement literature. People have tried various kinds of non-local attention and other mechanisms. So looking beyond the analysis and synthesis transforms, we can look at the model used to learn a distribution over the latents, so the entropy model. Going back to Bali 2017, the paper uses a factorized prior. So essentially, a histogram is learned per channel to model the latents in expectation across the training set. The implementation is pretty interesting because the histogram needs to be differentiable, but the end result is essentially a histogram. So this works pretty well, but it doesn't allow adaptation spatially. So it doesn't allow adaptation to the image content across the image. We had an ICIP 2018 paper that tried to improve on this. So it still learned a histogram. In fact, it learned a dictionary of histograms that could then be selected for different tiles across the spatial extent of the latents. So this allowed much more variation, but it was still a relatively basic model. It was still a histogram. And since you had to signal which histogram was used, there was a cost. And so as the size of the tile shrinks, the cost goes up. And so there had to be some kind of a balance. And ultimately, you can't go below about a 12 by 12 patch. Also in 2018, we had a paper that introduced a hyperprior. The idea here is to have a neural network predict a distribution for every element of y independently. So it's as if the tile size in the previous method was just a 1 by 1. What's nice here is that we're not just selecting from a dictionary of histograms. Instead, we're using a neural network to learn to predict a distribution. So the original paper at ICLR 2018 used a conditional Gaussian and just predicted sigma, the scale. And somewhat directly, there were papers after this that predicted both the mean and the scale. And then in Chang 2020, they predicted all of the parameters of a mixture model. So if there's 3 components, it's the mean, the scale, and the weight for each of those, so 9 total values. If we think about what information we have when we're trying to decode a single column in Y, for example, this orange location here, when we have the hyperprior, we actually have information about the entire tensor. So the causal context of of this location if you imagine a raster scan order, as well as all the locations that come after it, because Z is transmitted before any part of Y is decoded. But when we think about it this way, you can immediately think about the possibility of also conditioning this orange location on its causal context, for example, its local neighborhood. And this is essentially a pixel CNN. You would then decode by using the hyperprior as usual, but then taking this masked convolution and running it in raster scan order across the image. Then you would combine the information from the hyperprior and the spatial context with some additional network. The issue here, so it does turn out that the rate distortion performance of such a model is quite a bit better, and several researchers explored this. So we had a paper at NERPS 2018, Jan Klapp had a paper at BMVC 2018, and Judy Young Lee had a paper at ICILR 2019 looking at different variations of this idea, different ways of combining information from the spatial context and the hyperprior. But the issue with all of them and all of the work that builds on this is that when you just have the hyperprior, you can decode all of the locations of Y, all of the elements of Y in parallel. But when you use a pixel CNN type structure, you have to iterate in raster scan order, and you can only decode a location once its causal context is completely decoded. So the flops aren't necessarily higher, like the total amount of computation isn't necessarily higher, but you move from a parallel to a serial process. In an attempt to address this problem, so basically decoding is much slower in practice, we had a paper at ICIP last year in 2020 in which we tried to do conditioning in a different dimension. So typically you'd have your hyperprior, you'd use it to decode your latents Y, and what we say is split the Y tensor along the channel dimension, decode the first group, so the first set, in this case, of 3 channels, typically it would be more like 32 or 64, decode that conditioned on Z as usual, and then in a, you might say, autoregressive way, work your way down the group. So condition the second group on both the hyperprior and the first group, and condition the third group on the first 2 groups plus the hyperprior. So we have models that condition across the channel dimension, and we have models that condition across space, so the height and width dimensions. So it's no surprise that some researchers looked at methods that do both. So the obvious first thing to try is 3D convolution. So this Menser CVBR 2018 paper looked at this, and several others have combined it with a hyperprior in later work. But the idea is, if you're going to decode this gold location and it's in channel C, you can actually condition, if you're using 3D convolution, you can condition on the previous channel, so C-1 and all spatial locations. So that's perfectly reasonable and it works pretty well, except that if you're concerned about runtime, at least the serial nature of the decoding process, this has actually made it worse. So whereas before you were serial only in height and width, you're now going to be serial in all 3 dimensions. To remedy this, Chengyu Ma in a 2021 paper, a paper that came out earlier this year, combined the idea of grouping across channels along with spatial context. So in this diagram from their paper, you can think of the tensor being shown slice by slice, so the channels are increasing from left to right. In a spatial context only model, like our 2018 NERSC paper, you're decoding this red location only on its causal context in every channel. If you're going to look at 3D mass convolution, like in the Menser paper that we just talked about, you're going to ignore channels in the future, you're going to ignore everything that's more than 1 channel in the past, and you're only going to condition on everything in the previous channel in the spatial causal context in the current channel. And what Ma does is condition on all channels that come before the one that you're currently decoding. Now, in practice, what they do is break into 8 groups and only look at the previous channels in other groups. And in that way, you're not fully serial in all 3 dimensions. You're serial in space and height and width, but only, only serial across the groups in the channel dimension. So this is a very nice compromise. I'd like to move on now and talk about the rate distortion computation trade-off. Most of the research on learned image compression so far has really focused on the rate distortion trade-off, or possibly the rate distortion perception trade-off, as we'll discuss later. There are a few exceptions. I think the work coming out of Wave 1 is a bit of counterexample, they've discussed the runtime concerns of their image and video compression models. And more papers, especially in the last year, include runtime numbers. But I haven't seen a real analysis of what some of the trade-offs are and how much extra computation it takes to get some of the RD gains that we've seen recently. So this is a rate distortion graph for a variety of models. The rate distortion computation trade-off, of course, is three-dimensional, and what's not shown here is the computation part. So to make that a little simpler for analysis and visualization, the slides I'm going to present and the graphs I present are all going to show models, show results at 0.5 bits per pixel, and we'll focus on the Kodak dataset. So really this is just a slice in the RDC space. I also want to talk about PSNR. So all of the results are going to use PSNR as the distortion. This is a classic choice, but as most of you probably know, it's not the only choice, right? And it's probably not the best choice. There's an entire subfield, there's tracks, there's workshops on better perceptual metrics, there's learning-based methods, there's handcrafted methods, there's ensemble methods. I'm not trying to deny all of that. I chose PSNR because it's simple. I believe that most standard codecs have mostly focused on PSNR, although that's less true now. I know that AVIF, for example, uses some techniques that hurt their PSNR but boost subjective quality. I'm sure that's true for other codecs as well. Certainly JPEG XL uses Better Ugly, which was designed to be a better perceptual metric. Nonetheless, there is no single metric that I know of, or even an ensemble, that is sort of universally or even has a majority following as being the best perceptual metric. So I chose PSNR as a default. So this graph shows flops, and the units are thousands of flops per pixel, so these are not cheap models, against the PSNR, again, averaged over the Kodak dataset, so 24 images that are 768 by 512 at a half bit per pixel, so a moderate bit rate. We trained several hundred models to get this data, and then many variations within these three regimes of entropy models, as we discussed previously. So the models I circled here represent the ones that were actually published. So the architectures map and the architectures match, and the training procedure does as well. So I want to zoom in first on the factorized prior approach from Bali 2017 and dig into some of the differences, and then we'll explore the other models in more detail as well. So the change that I'm most excited about is a difference in how training occurs with regard to quantizing the latents. So we'll talk about this in more detail a little later, but basically we use a straight-through estimator during training instead of using additive uniform noise, as was described in the original ICLR 2017 paper. And what's nice is that since the architecture isn't different, it's just the training procedure, there's no additional computation for decoding, but we do see a pretty dramatic improvement in PSNR, so maybe 1.3, 1.4 dB just from this one change. So this is very exciting. On the other end of the spectrum, we can look at things like using a larger bottleneck, and we see here that the PSNR is about the same, but with a larger bottleneck, of course, there's more computation because there's more channels to compute and to process. In fact, and somewhat oddly, we see a decrease in the dB, very slight, but a small decrease in the decibels as we increase the size of the bottleneck. This shouldn't happen theoretically. Clearly, there's no capacity lost as we increase the size of the bottleneck. I suspect it's insufficient training. We trained for 2 million steps. Maybe we should have done 4 or 5. Nonetheless, I don't expect a major change even for the larger models. Along the same lines, these three variations have identical decoders, but larger encoder transforms. It does help. So increasing the depth of the convolutional layers in the analysis transform does lead to a better latent space, so better RD performance. It doesn't hurt decode speed. Of course, it increases encode speed slightly, which is not shown here. But the difference is quite small. If you look at the the y-axis, the labels here, this is less than 1/10 of a decibel, which is really not going to be perceptible, and it's probably not worth the extra computation. Zooming out a little bit, we can look at a wider range of models, still all within the basic architecture of using factorized priors. So here again, we've circled the published model, and we can ask, what do some of the models look like? Like, how are they different along the frontier? So along this frontier where we don't have any models that are faster, so lower flops, and better in terms of PSNR. So the published model, again, uses 192 channels in 4 convolutional layers. So we see this model I circled here only has 3 layers. It has, a higher stride, so we're doing more downsampling. It has smaller support. The published model uses 5x5 kernels in all layers, and fewer channels as well. So it's no surprise that it's faster, but of course it's also worse. So this is a true trade-off. As we move up the frontier, essentially we've increased the support here. So we're maybe 2x in terms of flops, but we have a nice gain in terms of dB. If we go to our 4th convolutional layer, but still smaller in terms of the number of channels in the published model, then we get another gain. And then things start to taper out a little bit. So now we have even more channels. What's nice here, however, is that we found quite a few variations that are essentially strictly better than the published model, right? So they have fewer flops, they're faster, and they have higher performance. And this is basically the trade-off of using this straight-through estimator idea during training gives us a boost in the quality of the model, and we can then compensate in part by using fewer layers or smaller channel depth to get a faster and better model. Zooming out again, we can include both the factorized prior models in blue below and the hyper-prior models, so from an ICLR 2018 paper in orange. And what we can see from this data is essentially the asymptote that you might expect. It's just lower than we might want it. So, of course, I'm not going to say that it's impossible, but none of the variations that we explored, even if we multiply computation, maybe from 10,000 flops per pixel up to 160,000 flops per pixel, none of these dramatically increase the quality. So there's some relatively low asymptote here. When we switch to a hyperprior, we get a nice bump, right? There's a large gap right here, but again, at some point there is an asymptote. Conveniently, it's much higher. But again, making the analysis and synthesis transforms larger, making the depths of different tensors larger, doesn't really break this fairly shallow asymptote. So again, we can zoom in on the hyperprior model and inspect some of the variations. We did sweep across a pretty wide range of nonlinear activations. As you might expect, it does make a difference, right? There's a pretty large gap between the best models, which use GDN, and the worst. I don't remember what this one actually is. It's probably sigmoid or tanh. GDN is a little more expensive. It includes a 1x1 com, but it's essentially swamped by the other transformations, so you can't even see it on this graph. And there are other choices that are quite similar. And looking at the hyperprior model, this is the kind of behavior we'd like to see. This is like the most exciting kind of variation, and if this were a published model, we'd like to see this model published, right? So what happened is we have a mild increase in flops. It's 2x, but we're still in the faster and smaller side of the spectrum with a fairly dramatic increase in performance. But beyond that point, when we further increase the complexity of the model, the size of the model, we just don't get very much. So here again, we're 3 or 4x in terms of flops, but we've only gained 0.2 dB, which maybe is visible, but we're on the cusp. Zooming out one more time, we can now contrast the hyperprior model with the channel conditional model. So this is the one where we split the latent tensor into multiple groups and condition later groups on the earlier already decoded one. And what we see is that there is overlap and there is a trade-off. So as we shrink the size of a channel conditional model,
the performance does not keep up with a larger hyperprior model. So below a certain speed, so here shown in flops, you want to use a hyperprior. You don't want to split. If you want higher quality and can tolerate slower models, however, there is a point where the hyperprior approach hits its asymptote, but by using channel conditional models, we can get better quality. So here it's only 0.22 dB, which isn't huge, but compared to some of the hyperprior models, we're both better and faster, which is what we want to see. And again, and probably as always, there is going to be some asymptote. So as we expand the size of the channel conditional model, we do see better performance in terms of PSNR, but it gets much slower. I think the models out here have maybe 8 splits. We tried out to 10, which is even slower. Since we did train hundreds of models, each of which are a little bit different, we can search for pairs that are identical except for a single kind of change. So here we're showing pairs that are identical except for the size of the kernels used in the convolutional layers. So it's either 4x4 or 5x5. What I was hoping is that this kind of analysis for this variation, for others, would uncover some interesting changes where, going up in the size of the kernel, for example, doesn't help very much. And so there's like a clear win in terms of RDC to use the 4x4. Unfortunately, that didn't happen in most cases. I can imagine an RDC trade-off where there's some beta parameter on C and that gives you a slope, and you can say, if for this model, the slope is steep enough that it's worth it, and maybe for this model it's not. But I don't see a way of making an objective sort of universal claim about when it's worth it and when it's not. Overall, going up to 5x5 does help. So the average here is about 25 extra flops, so thousands per pixel, for a 0.13 dB gain. You can decide whether that's worth it or not. I will say for most of our research, we have shrunk our models to get faster training times and thus turnaround times. And then when we want to publish sort of the best results, we'll train the final model with whatever sort of interesting sophistication it has with a larger kernel. So going back a little bit, the one change that did help across the board is how we handle quantization during training. So we found that for all of our models, all of the different kinds of entropy models and simple and complex analysis and synthesis transforms, we got a clearer win here. For some of the smaller models, maybe it wasn't as significant, but this is one of the larger, I think, 10 group channel conditional models. And this is a dramatic difference, right? It essentially takes the model from something that's not very interesting. It's barely better than a factorized prior-based model, sort of worse than a hyperprior model, but it turns it into something that is near state-of-the-art. Because this was the most clear win, we should go into a little bit more detail. So here's our basic autoencoder diagram once again. We have this quantization step, and as you probably know, the quantization itself is not differentiable. This is pretty easy to see. So in general, if you have some function y equals x, the derivative is 1, but as soon as you quantize, let's say we're rounding to integers, you now have this red curve, and the derivative is 0 almost everywhere. So the standard solution from this, from Ballet 2017, is during training you add uniform noise to approximate the effects of rounding, and then during inference you do actually round, you do quantize properly, since at inference time you don't need to backprop. Also at ICLR 2017, Tice et al. Published a paper that had a lot of similarities. One of the differences was that instead of using additive uniform noise, they used a straight-through estimator everywhere in their model. It's well motivated, but the end result was slightly worse rate distortion performance. More recently, there have been a few other approaches explored, and one that stands out is from Augustin 2020, and they look at a kind of soft quantization. So they use this somewhat more complicated formula to get a relaxation of full sort of hard quantization. It has this alpha parameter. I've graphed alpha equals 6,
And as you change that, as it gets smaller, you get closer to no rounding at all. And as it gets larger, you get closer to the effects of rounding. And so what they argue is you use this formula for soft quantization, and then you anneal the alpha value during training, so that by the end of training, you're very close to actual quantization, but you still have a gradient. Since the mixed approach of using additive uniform noise and a straight-through estimator in different parts of the model seems to work very well, I wanted to go into a little bit more detail to make sure it's clear what's happening. I should say this was first proposed, as far as I know, by Ju-Young Lee in an ICLR 2019 paper. And we used it in our ICIP 2020 paper last year as well. And the idea is that we're going to take Y and Z, so real valued latents, and during training we'll add noise when we're going to estimate the entropy models, so in these locations in this figure. And then separately, we'll go back to Y and round using a pass-through gradient. There's various ways of implementing that in TensorFlow or PyTorch, so that the input to the synthesis or the hypersynthesis transform is a rounded version of Y or a rounded version of Z. So those are the two locations where the different approaches, the additive uniform noise and straight-through estimator, are used. And I will say, I just found out that there's a paper at ICIP this year that's being presented on Wednesday from Tsuboda et al. That explores a variety of combinations of different approaches and is a nice follow-up and a more comprehensive study of the different ways of doing this. So you should check their talk out on Wednesday. So that's the first solution, or there's one solution to improving training of image compression models over just using additive uniform noise. A second that I think needs more exploration is to use soft quantization. Of course, you'll need to tune the annealing schedule. So, there's a recommendation in the paper. It's not clear how universal that is, or if it will, if the exact schedule needs to be adapted to a model. But I do think, this is somewhat speculative, but I do think this is the most principled approach of the ones I'm discussing. And then Guo, in this 2021 paper, Soft and Hard, Rethinking the Quantization in Neural Image Compression, introduced an approach where they train the model using additive uniform noise for some number of steps. Then they freeze the encoder and then continue training. So essentially they fine-tune using a straight-through estimator where only the decoder, so the synthesis and hypersynthesis transforms, are updated. And I think this is very well motivated in their paper. They look at some simpler problems, like I think MNIST coding, and that allows them to inspect the latent space. And they show that training the encoder with AUN gives better separation between the classes in the latent space, which makes a lot of sense to me. So far, I've only shown RDC results for learning-based methods, so I wanted to situate some of the results by showing the results from standard codecs as well. I don't have flop values for those, and of course many of them use integer operations, so there really aren't that many flops, but we can at least look at the PSNR values. Here we see that JPEG 2000 is about on par with our factorized prior models, and BPG and AVIF are both quite similar. They're on the upper end of hyperprior-based models, and the channel conditional is slightly better. However, if we plot more, including some other learning-based methods, we see VTM is quite high. I only know of 2 learning-based compression methods that are actually better than VTM, and this one only by a very small amount in terms of PSNR. But for these other learning-based methods, I also don't have the flop counts. We can, however, run the decoders and measure how long they take. So for this, the best channel conditional model that I have takes about 187 milliseconds on average to decode a Kodak image. For the top learning-based methods, they all use spatial context plus a hyperprior plus channel conditional groups. And with current implementations, the decode speeds are considerably slower. This is probably intolerable in terms of decoding a 512 by 768 pixel image. In VTM, at least on our machine, we got 77 milliseconds, so it's very, very fast in terms of decode. The encode can be a little slow, however. And to try to tie the two things together, so runtime and flops, we can plot both for our models. And we see a more or less linear relationship. So we have the number of decode flops, thousands per pixel along the x-axis, and the decode time in milliseconds along the y-axis. And we get a fairly linear relationship. And again, I plotted HEIF and VTM and libjpeg turbo, which is very, very fast. For a comparison. There are some caveats, of course. So all the learning-based methods ran on GPUs, oftentimes very high-end GPUs. The standard codecs ran on a CPU. And the decode time for the learning-based methods are isolated, meaning we didn't, for example, include the load time for TensorFlow, and we didn't include disk I/O, whereas that we weren't able to isolate that for VTM. So there's a bit of an apples to orange. So really the standard codecs are even a little better than they look here. Next, I'd like to talk about another research direction that I think is extremely exciting for learned image compression, which is generative compression. So we'll look at some of the challenges that are involved in training these models and talk about why high subjective quality is important. So we're back to our basic autoencoder figure and a rate distortion trade-off. And what we want to do here is change the story slightly by adding perceptual quality. And this is essentially in line with the Blau and Macaulay 2019 paper, where they talk about lossy compression in terms of the rate distortion perception trade-off. Conceptually, the way to think about this is we're going to have some input image. If we just train for rate and distortion, the distortion might be very good, meaning very low, but in this case it's blurry, so the perceptual quality is quite bad. So this will get a low mean opinion score in a typical rater study. If we train for high perceptual quality, but don't worry about distortion, we might get a beautiful, totally natural looking image that has very little to do with our input. So the distortion is quite bad, it's very high, but the perceptual quality, separate from knowing the input, is quite high. And so what we want to do, of course, is trade off both of these and have, not perfect, but very good distortion and perceptual quality. So here that's represented by an image that looks very much like the input. Maybe it's a little bit noisy, but it's not the kind of distortion like the blurriness in the second column that typically has low subjective quality according to raters. So to show a couple examples from HiFi-C, which is a generative image compression model from Menser et al. Published at NeurIPS 2020, so last year, we can look at this Kodak image and zoom in on the girl's shoulder. So this is the result from HiFi-C at 7 kilobytes, and it looks pretty good. If we look at the reconstruction from BPG at roughly the same bit rate, we see a much softer image overall and quite a bit of blurriness in this part of the sweater. If we double the bit rate, the result starts to get much better over here, but there's still quite a bit of sort of unnatural flatness on the left side. And when we pull up the original, what we see is the HiFi-C result does not perfectly match, right? There appears to be some yellow threads underneath that are just completely missing, even though BPG picked it up over here. But the overall texture appears correct. And, in my opinion, and this was borne out in the rater studies, this image is preferred to either of the BPG results. So we can look at some of the evaluation results for HiFi-C. And there's a couple things I want to focus on. First, the comparison is between HiFi-C at different bit rates. The same architecture without the adversary, so without the discriminator, so no GAN. A baseline model that doesn't use a GAN or LPIPs for training. It's just a mean and scale hyperprior. And finally, BPG as a representative of a standard codec. And the metric I want to focus on is this, the human evaluation. Part of the goal was to figure out how well some of the other perceptual metrics correlated with the human eval. And what they found was, at about a quarter bit per pixel, HiFi-C with the GAN was preferred compared to BPG, a little more than 2x the bit rate, and the mean and scales, or the learning-based baseline, at about 1.7x the bit rate. So that's a pretty significant difference. You can compare these two models where the only difference is, are you using the GAN or not? The bit rate is quite similar, and the answer is yes, you get a much better, here lower is better, human eval. Finally, we should talk about some of the failure cases. So Hi-Fi-C generates texture well, but it doesn't seem to understand a lot about semantics. So something that humans care about is other human faces, and we can see that in this reconstruction, these two boys' faces were not generated very accurately. Finally, I wanted to discuss a few promising research directions. So essentially research topics where I think there's an opportunity for significant progress in the next few years, and where I just think it's extremely interesting and worthwhile to explore. They fall out pretty naturally from the topics we've already discussed. So the first, based on the Hi-Fi-C results, is that I think we should target perceptual quality. And the background is essentially that improvements to rate distortion performance on mean squared error has slowed, and it increasingly comes at great computational cost, as I showed earlier. So we could continue to push in this direction, but barring some major breakthrough, I think that we should instead focus on the perceptual quality through generative decoders, and I think large gains are still possible there. So the key research questions would be, how can we tailor learning-based methods to, the quirks of the human visual system? So I know there's some papers, for example, that look at intelligent ways of incorporating chroma subsampling as an easy example into learning-based methods, but I think we're far from exhausting the opportunities in that direction. Similarly, we can look at ways of effectively incorporating semantics and saliency into models. The saliency, actually both semantics and saliency play into the Hi-Fi-C failure case where we saw good textures generated for the barn door and a sweater, but not a face, which is arguably much more important in the vast majority of pictures. And finally, how can we design perceptual metrics that are as effective as GAN? So the adversarial loss and the discriminator helps us train a model, but it doesn't necessarily give us a good way of measuring how good it's doing in terms of perception. Of course, the desire for a better perceptual metric is quite broad and deep and needed in almost all areas of image processing. So this is hardly new, but I'd like to focus on the GAN aspect of it. And then, in this area, my speculative prediction would be that learning-based methods are not going to significantly outperform hand-engineered codecs like BBC and AV2 when focused on PSNR. Can we outperform? Sure, but we're going to use 100x more compute or 1,000x more compute, and it's not going to lead to a deployable codec. However, if we focus on perceptual metrics, we have some machinery now through GANs. Starting in, say, 2016, so not exactly new, but they haven't been applied that much to the compression problem. So we have machinery to train models to reconstruct images with much higher subjective or perceptual quality. And the second direction is to focus on computational cost. So if improvements to RD performance are coming at greater and greater computational cost with larger models and slower models, instead we can focus on RDC trade-offs. Essentially, I see much of the work in the field as looking at better but bigger models. What I'd like to see instead is more focus on methods that are faster and near state-of-the-art. This leads to a few key research questions. For example, how can we build asymmetric models, more computation in the encoder and less in the decoder? Typically, we see pretty symmetric models when it comes to learned methods. One really nice counterexample is work by Yibo Yang, Bamler, and Mont from 2020. And one of the things they explored in that paper was the fact that the encoder learns to map images into a latent space that's good in expectation, but there's no guarantee for any particular image that this mapping will be ideal. And so, again, one of the things they explored in their paper was a method of per image during the encode process optimizing, directly optimizing the latents, based on the particular image you're going to encode. And what they found is they got a much improved rate distortion performance, a nice gain there. The decoder doesn't change, so it's not slower at all, which is great. Unfortunately, the optimization is truly, a few, hundreds or thousands of steps of gradient descent. So I think they were roughly 1 minute or so to encode a Kodak image. So that might be slower than what most people can tolerate, but I still think it's a very creative idea and sort of points in one useful direction in terms of how to make the encoder slower without hurting the decoder and still seeing a huge RD gain. Another question focuses on hardware. So how do we best utilize the massive parallelism we have with GPUs and TPUs? And the hardware has its own quirks. So FP16 is quite a bit faster than FP32, for example, and certain hardware is faster if you have a particular sparsity structure, et cetera. So can we learn models, and can we engineer our models to take advantage of the hardware? And finally, can we implement conditional execution? So this was talked about in this paper, outrageously large neural networks, where essentially there's multiple paths through the network, but instead of running them all and coming to the right answer, you only run certain ones. So in this paper, the network would learn to predict which path you would take. But in a compression framework, you can imagine the encoder figures out, either through a learning method or through some kind of a search, which path is best for a particular image. And then the decoder ends up doing much less work. And my speculative prediction for this is that essentially faster hardware will not compensate for the best or slowest published models, especially if we continue on the current path where we have much slower, 10x slower models for a relatively small RD gain. So we're going to need conditional execution or some kind of asymmetric model to have practical decode speeds. And to briefly summarize, we've seen significant rate distortion progress for learned image compression over the past 5 years. We're now on par with the best standard codecs on PSNR and quite a bit better for other metrics if you optimize for those metrics. But this progress came with significant computational cost. So these best models are much, much slower than they need to be for practical deployment. So future research should look at the rate distortion computation trade-off and not just the RD trade-off. And even if we get models that maybe aren't state-of-the-art in the strict RD sense, if they're showing interesting results or insightful methods for speeding up decoding especially, or encode and decode, they should be accepted at conferences and we should learn from them. And the other direction that I think is most promising is to look at subjective and perceptual quality. And using GANs or other methods like diffusion models are pretty interesting and offer an alternative to GANs. Or semantic, some of the generative results from DALI that came out earlier this year, where it's essentially text to image generation, is super exciting, and trying to incorporate that kind of global conceptual information into our learned methods seems very promising. Okay, thank you. We should now have time for some live Q&A.